Okay, so here's a quick overview of magnets and magnetic fields. Before we replaced a refrigerator, well, even now, our refrigerator magically gets covered with magnets, and you guys have all played with magnets, but here's some little bit of facts just to kind of get you into the physics part of what a magnet is. And so magnets always have two poles. There's a north pole and a south pole, and you're going to see a lot of similarities as we talk about magnets between electricity and magnetism. You've got to keep the idea between poles and charges separate. So poles and charges are not the same thing. Earth is a bar magnet. It's a big, giant bar magnet with a magnetic north pole near the geographic south pole. And I'll show you a picture of this in a minute to kind of give you that idea. But we're basically living in a magnet. And then Ørsted, one of the names that you don't hear much with physics, actually discovered that when you put a compass needle near a current-carrying wire, the compass needle flicks or moves. And it turns out that he discovered the idea of a magnetic field, so that field around the magnet that we know attracts and repels. So like I said, magnets have two poles, a north pole and a south pole. And they're created by tiny magnetic dipoles aligning within the material. So if you can imagine, every magnet is made up of teeny tiny magnets, and they're all lined up, and that's what creates a magnet. And opposite poles attract and like poles repel. So if a north and a south are going to attract, and a north and a north are going to repel, and a south are going to repel. Interestingly enough, because of the makeup of a magnet, you can cut a magnet and create two smaller magnets, each one with a north and a south, and cut it again, and it's a tinier magnet with a north and a south, and just keep going and going and going until you get down to the microscopic level. And eventually you lose magnetism because you either have a north and a south, or you don't have a magnet, because you can't have what they call a magnetic monopole. So there's only dipoles. And these magnetic poles produce a magnetic field. And we're going to call the strength of the magnetic pole strength, and it's got a variable of a little small letter p, and it is measured in ampere meters or amp meters. So like I was talking about the inside of the magnetic material, the ferromagnetic materials are strongly affected by magnetic fields. So these are things like iron, cobalt, and nickel. They stick to magnets, and that's kind of when you do your labs back in elementary school, or play with magnets when you're a little kid, you figure out what sticks to a magnet and what doesn't. And those things would have been made out of iron, cobalt, and nickel. And these materials can be placed in a magnetic field and cause all of the magnetic domains actually to align. And when they line up, they create a magnet. And when they line up and stay lined up, they're called a permanent magnet. Magnets, while we call them permanent, can also be demagnetized. And when you're working with magnets, you have to be careful. You don't want to place them near a magnetic field. And if you have credit cards or other things with that magnetic strip on the back and it gets demagnetized, that's probably what's happened to it, is you placed it near something else that has a strong magnetic field. You can also, with a standard magnet, you can drop it or heat it. And what that does is it causes all of those little magnetic domains that are lined up nicely to just scramble up. So you don't have a magnet anymore. Like I said, the area around the magnet is surrounded by a magnetic field where you would experience a magnetic force. And if you've ever played with some of the stronger magnets, you can feel them repel each other. You can feel them pull together. That magnetic field strength is measured in something that we call Teslas or Gausses, depending on which set of units that you're using. Just to know, what's strong and what's weak. Strong magnetic fields are 2 to 10 Teslas, and the Earth's magnetic field is actually 5 times 10 to the minus 5th Tesla. So we don't really feel it We know that there are animals that can sense it, and there's been some research about can you feel it, which is kind of interesting. Do you know how to sense a magnetic field? So that's kind of an ongoing. But here's some pictures of magnetic fields, and they might look familiar if having just finished up the electric field lessons. The magnetic field is in the direction that an imaginary test North Pole would go. So you can imagine that you dropped an imaginary pole that's just a North Pole, which can't exist, into the field, and the direction of the field represents which way it would go. Field lines are continuous loops. They are going to always connect, and even if they look like they're going off the page, they're just getting weaker, but they do connect eventually. Just like the electric fields, the number of lines and the concentration of lines tells you how strong it is. It's stronger near the poles and weaker as you move away from the poles. And earlier I said that the Earth is a big magnet, and the North Pole of the magnet is pointed at the South Pole of the world. So it's a little bit upside down. If you have a compass, if you've ever played with a compass, this is why the North Pole of the compass points north, is because it aligns with the magnetic field. The magnetic north is not exactly in the same spot as geographic north. It is in the northern part of Canada. So when we're talking about magnetic fields, we kind of have to talk about current, because when you go back to look at the discovery of the magnetic field, Ørsted discovered the magnetic fields by placing a compass near a wire that had a current flowing through it. And he discovered that that compass would deflect, and it showed the shape of the field around the wire. And he found that current carrying wire is surrounded by a magnetic field. So anytime electric charges are moving, there's going to be a magnetic field. And we use that for a lot of different things. One would be creating an electromagnet. If you take that wire and shape it into a coil or a spring-like thing, you get an electromagnet. We also have solenoids that we put into circuits. There's MRIs, there's maglev trains, and there's a lot of other applications that use the idea that magnetic fields and electricity interact with each other. And we'll talk about some more of those in some other lessons. Alrighty, bye-bye.